Well, thanks. So I have to admit, many things have been said already. So that's more going to be a use case here, and it's very much a work in progress. So you might be disappointed compared to all the nice stuff we've seen in the first part, but it's a workshop, right? So that's a workshop in progress, let's say. So a few words about RTK. So initially, RTK was an open source and cross-platform software for fast circular convex city reconstruction based on the Insight toolkit. It's been released first in 2012, I think. So it's a bit old, not as old as Steer, but it's oldish. And over the years, while doing research with this tool, we added many functionalities, 4D motion composited CT and spectral CT mainly. We also extended to other modalities like SPECT, etc. There are others I'm not mentioning. And yeah, it's an Apache 2 license. It's GitHub hosted. It became, I think, 10 years ago, something like that, a remote module of ITK. So ITK is this big software infrastructure where you can add modules. And I made RTK such that it is one of these modules. It's multi-threaded CPU and CUDA-based GPU code. It is used mainly via command line tools, at least historically. It's written in C++, and since also about the same time as the remote module, I added Python wrapping that came as a bonus with it being a remote module of ITK. And it's used by quite a few teams around the world, mainly teams using it for convex city reconstruction. So RTK and PyTorch, it doesn't have such a big history. So to my knowledge, RTK has not been integrated in machine learning models so far. It's only been applied pre or post reconstruction. Several projects are starting, at least in Lyon, which aim at using RTK in machine learning models, such as plug-and-play unrolling approaches. And the first step that I present now is to efficiently link the RTK data structures to PyTorch tensors. We usually deal with quite large data, and so we don't want to have these device to host memory copies all the time. And like I said, it's a work in progress. So I need to say a few things about the data structures used in RTK. So it's mainly using the ITK image type, which is templated over the pixel type and the dimension of the image. And like it's been a bit discussed previously, it's mainly a buffer plus metadata, and the metadata position the image in space, so that's the origin, spacing, and direction, as well as provide this region mechanism, which is used for streaming data or for only buffering part of the data in the memory using some sort of out-of-core processing. I'm not going to explain this. It's not a very simple mechanism, but that's part of the metadata of the image type. And when you wrap that in Python, you end up with a dictionary for a number of predefined pixel types and image dimensions. And ITK provides conversion from and to NumPy arrays. So either just views of the array or of the image, or a copy of the array of the image. And it seems to me that that was a bit the sense of my questions before, that since we have a view of an ITK image in a NumPy array, we can directly convert this to PyTorch on the CPU. But that's for the CPU side, and the next step in the implementation is how can we implement GPU tensors. So I need to say a few words about the CUDA data structure. So at the time we implemented this, there wasn't any unified memory. So we had our own data manager. So an ITK CUDA image inherits from the ITK image. So it's just an ITK image plus one data member, which is the data manager. so the architecture of this is based on the GPU image in ITK, which is similar but for OpenCL. And so the members of this data manager are the CPU buffer, the GPU buffer, and then flags which tell us whether the accurate data are on the CPU or on the GPU side or both. And the idea behind this is to only transfer memory from CPU to GPU when necessary, so that you don't keep copying data from the CPU to the GPU and backward. So the Python wrapping is very similar to the ITK image. So it's also a dictionary for a number of predefined pixel types and image dimensions. And the conversion to a torch tensor, which would be on the GPU, is what I'm going to talk about. And I guess I hadn't listened to Casper's presentation before, so we decided to try the CUDA array interface, which seemed to work well for us. So the CUDA array interface, in the words of Nimba, is created for interoperability between different implementations of CUDA array-like objects in various projects. And the idea is borrowed from the NumPy array interface. So what you actually do is simply add a member CUDA array interface to your Python class, which returns a dictionary that must contain the following entries: the shape, the type string, the data, and the version. So currently our status for the implementation of this is we have asked Kitware, with whom we work, to implement the CUDA array interface for CUDA images. So you can have a look at this online. But basically, what that does is simply create the code for all the types and shapes of this CUDA array interface dictionary. So the CUDA array interface is seems quite interesting to us because it allows communication with many different libraries, including PyTorch and QPy, for example. So initially, Kitware tested it with QPy, and I tested it with PyTorch for this presentation. A very simple basic example. So at the top here, so it's a Python example. I create a CUDA image which has a given shape allocated, and then since my ITK image object has this CUDA array interface, I can just say torch as tensor ITK image, and this will return me a torch image. So due to the memory layout, it actually changes the orders of the dimensions, but that's something we are used to in ITK when we deal with NumPy images. And just for this example, what I tried is modify the buffer of this torch image and then simply write this ITK image after modifying the buffer with torch and not with ITK. And indeed, if I look at this ITK image, which is written on disk, it has modified the torch, has modified the buffer without any memory transfer. It directly changed the ITK image CUDA buffer. So that was it. That was quick. I didn't have too much to say. So ITK can efficiently convert an ITK image to an NumPy array and hence to a CPU PyTorch tensor. We started with the implementation of the CUDA array interface in this CUDA common module, which implements the CUDA images. We are currently still missing an implementation of on the ITK image side, which would translate an array interface to a CUDA image. As is done in Python by QPy. So you have, this is a link and you can go have a look at what QPy, how does QPy do it. And this is also done in C++ by ITK for NumPy array. So we simply need to choose whether we do it in Python or in C++ and implement it. So this is very much a work in progress. The implementation of RTK operator in NN modules will be the next step. And the way I foresee this is we will do it ad hoc. So for a given kind of reconstruction, for example, spectral CT, we would implement the torch tensors using the RTK operators without any data transfer between CPU or GPU or even within the GPU thanks to this CUDA array interface. This is something we are currently exploring with other people at the lab in Spirit, which is a toolkit for inverse problem investigations developed in my lab. And that's it. If you have any questions, happy to take them.